Langchain Postgres Chat Message Histories. This section describes a langchain tool that leverages a PostgreSQL database to maintain a persistent record of chat messages. Inputs. This tool accepts a chat message history as input. The chat message history typically includes information like user queries, bot responses, timestamps, and potentially other relevant data. Outputs. The output of this tool is the chat message history successfully stored in the designated PostgreSQL database. Steps. The first step involves creating a table within the PostgreSQL database to specifically store chat message history. This table would typically include columns for storing user queries, bot responses, timestamps, and any other relevant data. The second step involves writing a function or procedure that facilitates the insertion of new chat messages into the previously created table. This function should handle the validation and formatting of data before inserting it into a database. The final step involves using the function created in the previous step to insert the chat message history into the database. This step ensures that the chat history is persistently stored within the PostgreSQL database. Prerequisites. A PostgreSQL database is essential for storing the chat message history. This includes a database name, which is the name of the specific database instance used, and a table name, which is the name of the table within the database that will store the chat messages. For example, a database named Chat History DB might contain a table named Message History. The langchain library is crucial for implementing this tool. A specific version of the langchain library is recommended for compatibility and to ensure that the functionality of the tool is consistent with the library's capabilities. Fine-tune parameters. The database connection details are required to establish a connection between the tool and the PostgreSQL database. These details usually include the database host, database name, username, and password. Challenges and fixes. Database connection errors can occur if the provided database connection details are incorrect or if the PostgreSQL database is not accessible. To resolve this, check the database connection details, ensuring that they are accurate and that the database is running and accessible. Table creation errors may occur if the user lacks sufficient permissions to create tables in a database or if there are conflicting table names. To resolve this, verify the user's permissions in the database and make sure that the table name is unique within a database. Data insertion errors can occur if the data being inserted into the table is not in the correct format or data type. To resolve this, check the data types of the columns in the table and ensure that the data being inserted is formatted correctly to match those data types. Langchain Postgres Vector Stores Distance Strategy defines how distance between vector embeddings is calculated. This strategy determines how similar two vectors are, which is crucial for finding the most relevant information in a vector database. The chosen distance metric impacts the effectiveness of the search, as it governs how the similarity is quantified. Inputs. Embeddings from the model. These are numerical representations of text, images, or other data generated by a machine learning model. They capture the semantic meaning of the input data, allowing for more nuanced comparisons than traditional keyword-based searches. Existing embeddings in the database. These are the pre-computed embeddings of the data already stored in the database. They serve as reference points for comparing new embeddings and finding similar items. Outputs. Ranked list of relevant embeddings. This is the output of the distance calculation, presenting the most similar embeddings from the database to the input embedding. This list is ranked based on the calculated distance, with the most similar items appearing at the top. For example, in a question answering system, this could be a list of relevant passages that are ranked based on their semantic similarity to the question. Steps. Calculate the distance between the query embedding and the database embeddings. This involves applying a chosen distance metric to compare the input embedding with each embedding. In the database, the distance metric quantifies the dissimilarity between two vectors. For example, the cosine similarity measures the angle between two vectors, with smaller angles indicating greater similarity. Sort the results based on the calculated distances. After calculating the distances between the input embedding and all database embeddings, the results are sorted according to the calculated distance. This process ensures that the most similar embeddings are presented first in the output, providing a ranked list of relevant information. Prerequisites. Install the necessary package. This step involves installing the langchain package, which provides the necessary tools and libraries for working with vector databases and embedding models. Define a distance metric. This step involves choosing a distance metric that best suits the specific use case and data. Common distance metrics include cosine similarity, Euclidean distance, and Manhattan distance. Each metric measures similarity differently, impacting the ranking of the retrieved embeddings. Fine-tune parameters. Distance metric. This parameter allows you to customize the distance metric used to calculate similarity between vectors. By experimenting with different metrics, you can improve the accuracy and relevance of the retrieved embeddings. Top K results. This parameter specifies the number of top-ranked embeddings to be retrieved from the database. By adjusting this parameter, you can control the number of results returned, balancing the trade-off between retrieval speed and comprehensiveness. Challenges and fixes. Slow retrieval due to large database. This issue arises when the database contains a massive number of embeddings, leading to slow retrieval times. To mitigate this, you can use an optimized database engine, like PostgreSQL with its efficient indexing capabilities, or reduce the number of embeddings stored in the database. Inaccurate results due to poor embedding quality. This problem occurs when the embeddings are not representative of the underlying data, leading to inaccurate similarity calculations. To address this, you can use a higher quality embedding model, one trained on a larger and more diverse dataset, or fine-tune the existing embedding model on your specific data to improve its accuracy and relevance. Langchain Prompty Core Front Matter Summary. A comprehensive description of langchain Prompty Core, a framework for developing and managing applications powered by large language models (LLMs). It offers a range of tools for defining prompts, organizing data, and deploying these applications. Inputs. A template for the prompt that will be used to guide the LLM in generating responses. This can be a basic structure or a more complex template that incorporates variables or placeholders for user input. The data that will be used as input to the LLM. This could include text, code, or other structured data relevant to the task at hand. Outputs. The raw output generated by the LLM in response to the provided prompt and input data. The LLM output formatted and presented in a way that is suitable for the intended use case. This might involve extracting specific information, structuring the output, or adding visualizations. Steps. Defining the prompt. This step involves creating a clear and concise prompt that guides the LLM towards the desired output. This can involve crafting a template, incorporating variables, and carefully selecting the appropriate tone and language. Providing input data. This step involves supplying the LLM with the relevant data it needs to generate a meaningful response. The format and content of this data should be carefully considered to ensure accuracy and relevancy. Generating LLM output. This step involves interacting with the LLM and providing it with the defined prompt and input data. The LLM will then process the information and generate its output, which can be text, code, or other forms of data. The formatting output. This step involves taking the raw LLM output and presenting it in a way that is useful and understandable for the intended audience. This could involve extracting specific information, organizing the output into a logical structure, or adding visual elements. Prerequisites: installing the langchain library, which provides the necessary tools and functionality for building and managing LLM-powered applications. This can be done using the following command: pip install langchain. Access to a large language model LLM via an API, such as OpenAI's Application Programming Interface API. This requires obtaining an API key from the LLM provider. Fine-tune parameters. Prompt engineering. This involves crafting prompts that are effective at eliciting the desired output from the LLM. This might involve experimenting with different wording, structures, and the inclusion of relevant context. LLM selection. Choosing the right LLM for the task at hand. Different LLMs have different strengths and weaknesses, so it's important to select one that is well suited for the specific application. Challenges and fixes. Prompt ambiguity. When the prompt is unclear or open to interpretation, the LLM may generate responses that are irrelevant or unhelpful. Refining the prompt by adding more context, providing specific instructions, or using clear language can help to reduce ambiguity and improve the accuracy of the LLM's responses. LLM output inconsistency. LLMs may sometimes generate inconsistent responses to the same prompt, even with the same input data. Improving the quality of the input data can help to reduce inconsistency by ensuring that the LLM is provided with accurate and relevant information. Slow execution time. LLMs can be computationally expensive, and processing complex prompts or large amounts of data can take a significant amount of time. Optimizing code can help to improve execution time by streamlining processes, reducing unnecessary steps, or leveraging more efficient algorithms. Output formatting issues. The raw output generated by the LLM may not be in the desired format for the intended use case. Enhancing formatting logic can address these issues by applying specific rules or algorithms to transform the LLM's output into the desired format. This might involve extracting specific information, structuring the output, or adding visual elements. Langchain prompty core summary. A Python library that simplifies building powerful large language model LLM applications by combining langchain and prompty. Langchain prompty core summary leverages the strengths of both libraries, providing a comprehensive toolkit for developing LLM-powered applications. Inputs. Large language models LLMs. Powerful AI models capable of understanding and generating human-like text, such as GPT-3, Lambda, and Bloom. LLMs are fundamental components in building LLM applications, providing the core intelligence for text generation, translation, summarization, and other tasks. Prompts. Instructive text inputs designed to guide LLMs towards specific outputs. Prompts play a crucial role in shaping the behavior of LLMs, allowing users to specify the desired format, style, and content of the LLM's response. Data sources. External databases, APIs, or files that provide context and information for LLMs to process. Data sources enable LLMs to access and integrate real-world data, enriching their understanding and making them more adaptable to diverse tasks. Outputs. LLM outputs the text generated by LLMs in response to prompts and data inputs. LLM outputs represent the core results of LLM applications, providing users with valuable insights, creative content, or automated responses. Steps. Define prompts. Carefully craft prompts to guide LLMs towards desired outputs. Prompt engineering involves understanding the nuances of LLM behavior and crafting effective prompts that elicit accurate, relevant, and high-quality responses. Integrate with LLMs. Connect LLMs to your application using appropriate API keys and configurations. LLM integration involves configuring the chosen LLM and establishing communication channels for sending prompts and receiving generated responses. Connect to data sources. Establish connections to external data sources to provide context and information to LLMs. Data source integration involves setting up data access mechanisms, extracting relevant information, and efficiently feeding it to the LLM for processing. Run and manage chains. Orchestrate the execution of prompts, LLMs, and data sources to achieve complex tasks. Chain management involves designing workflows, managing dependencies, and coordinating the interactions between different components of your LLM application. Prerequisites. Python, a general-purpose programming language widely used for data science, machine learning, and web development. Python's flexibility, extensive libraries, and active community make it an ideal choice for developing LLM applications. Python 3.8 or higher requires a specific version of Python for compatibility with the langchain and prompty libraries. Langchain, an open-source Python library that simplifies building LLM applications by providing tools for chain creation, data integration, and LLM interaction. Langchain's modular architecture and rich set of functionalities make it a valuable resource for streamlining LLM development. Langchain 0.0.142 or higher requires a specific version of Langchain for compatibility with the library's features and dependencies. Prompty, a Python library focused on prompt engineering, offering tools for building, testing, and managing prompts. Prompty's emphasis on prompt design empowers developers to create effective prompts that elicit accurate and relevant LLM outputs. Prompty 0.1.2 or higher requires a specific version of Prompty for compatibility with the library's features and dependencies. Fine-tune parameters. LLM model. Select the appropriate LLM for your task, considering factors like model size, training data, and specific capabilities. Choosing the right LLM is critical for ensuring the quality and relevance of the generated outputs. Prompt engineering. Refine and optimize prompts to maximize the accuracy, relevance, and creativity of LLM outputs. Prompt engineering is an iterative process that involves experimentation, feedback analysis, and continuous improvement to achieve desired results. Data source configuration. Configure data sources to provide the right context and information to LLM's. Data source configuration involves defining data access methods, filtering relevant data, and formatting it appropriately for consumption by the LLM. Challenges and fixes. Error handling. Implement robust error handling mechanisms to gracefully handle unexpected situations during LLM execution. Error handling involves detecting potential issues, providing informative messages, and recovering from errors to maintain application stability. Implement robust error handling mechanisms. Develop code to detect and handle errors, preventing application crashes and ensuring smooth operation. Performance optimization. Optimize code for efficiency and reduce execution time to improve speed and responsiveness of LLM applications. Performance optimization involves identifying bottlenecks, utilizing efficient algorithms, and leveraging hardware resources to enhance application performance. Optimize code for efficiency and reduce execution time. Implement techniques like code profiling, data preprocessing, and parallelization to improve the execution speed of LLM applications. LLM integration issues. Ensure proper application programming interface API keys and configuration. For LLMs to enable seamless communication and data exchange, LLM integration issues can arise from incorrect API keys, network connectivity problems, or misconfiguration of LLM parameters. Ensure proper API keys and configuration for LLMs. Verify the accuracy of API keys. Ensure stable network connections, and carefully configure LLM parameters to establish proper communication and data flow. Langchain Prompty Core Model Settings Summary. Langchain Prompty is a framework for building conversational artificial intelligence applications, encompassing user interaction, context management, and output generation. Inputs. This is the raw input provided by the user, serving as the starting point for the conversation. For example, a user might type a question or a request. This refers to the collected information from previous interactions, forming a context for the current conversation. It includes the history of user input and generated responses. Outputs. The generated text represents the response provided by the conversational AI system based on user input and context. These are the specific actions that the conversational AI system needs to perform as a result of the user interaction. It could involve retrieving information, sending notifications, or other actions based on the conversation's context. Steps. This stage involves processing the user input, including cleaning, sanitizing, and interpreting the intent behind the input. This involves accessing and retrieving relevant information from the accumulated context or external sources to provide a more comprehensive and informed response. This refers to the process of selecting the appropriate language model based on the nature of task and user input. This stage involves crafting and formulating effective prompts, tailored to guide the chosen language model to generate accurate and relevant responses. This involves executing the selected language model with the constructed prompt, generating the output based on the model's capabilities. This involves formatting and presenting the generated response in a user-friendly and coherent manner, making the output easily understandable. Prerequisites. Python 3.7 or higher is the required version of the Python programming language for running langchain prompty. Langchain library is a Python library that provides essential components for building conversational AI applications, making it a core requirement for langchain prompty. A language model such as GPT-3 is essential for providing the core capabilities of language understanding and generation within langchain prompty. Fine-tune parameters. Temperature parameter controls the creativity and randomness of the generated responses, allowing fine-tuning the balance between predictable and unexpected outputs. Top K parameter restricts the model's output to the top K most probable tokens, limiting the diversity and potential creativity of the response. Top P parameter restricts the model's output to a subset of tokens with a cumulative probability of P, controlling the balance between diversity and coherence of the response. Challenges and fixes. Incorrect model selection can result in inappropriate or irrelevant responses. To address this challenge, ensure the selection of a language model that is appropriate for the specific task, considering its strengths and limitations. Prompt ambiguity can lead to misinterpretations and inaccurate responses from the model. To address this challenge, craft clear and concise prompts that explicitly guide the language model towards the desired output, avoiding any room for misinterpretations. Model hallucination refers to the model generating false or fabricated information, lacking factual accuracy. To address this challenge, implement mechanisms for fact-checking the generated responses against reliable sources, ensuring the output aligns with reality and truthfulness.